So since we are processing the extended Gerber format, so the first requirement of the project is to prepare an extended Gerber format file. We have chosen Eagle from CADsoft USA as one of the many available CAD softwares. So what we have opened over here is a sample Eagle layout file which has been created earlier. So this is a layout file, as you can all see. So pulling on the rashness, this gives us the blue area is the active copper area and the green area are the patch and wear. So basically it is a single layer, which this is the bottom layer layout file. So what we will be doing is we will be running the CAM processor, and this will generate the required Gerber file for this particular layer. So we'll be running the CAM processor, we'll be selecting a job, we'll be selecting the extended Gerber file format, the Gerber RS274X CAM, and here we'll be selecting, basically it's the bottom side, so the bottom pads and vias. So, and we have selected the extended Gerber format, Gerber RS274X, and we will be giving the output file name. So I'll be saving this file on the desktop by the name of PROJ, and we will process this job. And so basically it has been processed. So as you can all see, the proj.cmp, which is the extended Gerber file, has been created onto the desktop. So basically it's just a text file. So when we open it, so this is the Gerber file. So on seeing the Gerber file, it is quite clear that it is basically a text file which consists of a lot of coordinate data, exactly to be precise. So what we have on top here is the format specification, basically on what coordinate data the CAM processor has processed, whether according to inches or it has processed and everything. Here we have all the predefined standard apertures and all the user defined apertures that have been created in the layout file. And here we have is the extrapolation of the apertures to create the final image. So we have for aperture, now see there has been some extrapolation of 3 coordinates. Similarly for D12, some extrapolation has been done some number of times. So on repetition and reconstruction from these coordinate data, the final layout can be reconstructed. So basically, as we can see that the Gerber file is nothing but a simple coordinate text file itself, in which every line of the text gives a specific coordinate, and upper part of the Gerber file gives us the format specification according to which the Gerber file has been created. So currently, due to the inavailability of the NI MyRio for demonstration and as a proof of concept, the current progress is made on an AVI device, the ATmega32. So shown here is the current setup arrangement, and I'll briefly explain what each part is individually doing. We are using the FT232RL as the USB to UR conversion medium. So here we are using the onboard FT232 present on an Arduino Duo Milano board. This here we have constructed an ATmega32 development board which houses the program of receiving the UR data and generate output for stepper motor. The board has port A, port B, port C and port D. The microcontroller houses the program for receiving the UR data and generate output for the stepper motor. Here we have is the motor driver for the stepper motor, and we have used the L293D motor driver IC, which is a dual H-bridge IC powered at 8 volts. So the 8 volt it is harnessing from the direct 7808 available on the ATmega32 board itself. And right here we have a standard 4-pole stepper motor connected to the motor driver just for the sake of demonstration. So this right here is the program code that is flashed on the AVI device. The program is created on WinAVI using embedded C. The program code is pretty simple in itself, and as all it takes is a predefined format of data as it can be seen here. So first of all, this code fragment right here is processing of the anti-clockwise or clockwise fashion of the stepper motors as it can be seen. This has been a function has been created, anti-step for anti-step rotation and step for stepwise rotation. So what this complete program does is it takes a predefined format of data through UR. So as it can be seen right here, that first it will accept data C or A for clockwise or anti-clockwise. Then it will delay for a small instance of time on which it will be ready to accept other data. So the next data for it should be T, and if it does not receive T in the next 10 milliseconds, it will be invalid. So the next data it must receive would be T, and then it receives T, it will then wait for 3 more characters of data, which must be numbers exactly. So what will they do is that they will be reconstructed back to create the delay. Delay is actually the steps, the delay in milliseconds between each particular step, whether clockwise or anti-clockwise of the stepper motor. And after the delay, it will wait to receive the character S, and S is basically for the steps. And because we would be specifying the number of steps is that it has to execute, whether clockwise or anti-clockwise. So after the 3 numbers from T, it will be, here the delay has been calculated. Here it is accepting after for S, and then after S it is accepting 3 more data, which will be numbers, on which it will be calculating the number of steps to execute, which were earlier specified based on clock. So now with the concerned make file, make clean, and then it will be compiled with the concerned make file, which is the make file for the atmega32, and the relevant hex file is generated. This hex file is flashed onto the flash memory of the microcontroller. So here we have is the hex file. The hex file has been created, and this particular hex file will be flashed onto the flash memory of the microcontroller.
So now basically what we need to understand is that how to construct a track out of the given coordinates which are extracted from a Gerber data. So the following image can be used to explain this. So what the Gerber data usually gives us is, means here we have assumed a small track. It is a track. Basically this will be the active copper region. So what the Gerber file gives us is that for every coordinate it gives us the centers of the track. So if we consider the circle as a standard aperture, so if we extrapolate this circle from x to y2 to x to y1, what we'll be basically getting is this complete track. So basically we need to create a VI that gives us this kind of shape, this oval capsule kind of shape, and then later on we can compile many of these to compile many tracks, means to reconstruct a complete track. So this is basically the element of a track. What the Gerber file gives us is, it just gives us the center of the tracks, means the Gerber file will give us the value of x to y2 and x to y1, which is basically of no use to us because it will give us just a single line. But what we want is a track of width d. The width can be extracted from the Gerber file aperture itself, for which particular aperture that track is being extrapolated. So once we have x1 y1 and x2 y2, we can have the line basically, and when we get the line, it is easy to calculate the slope of this line with respect to the positive x-axis. So suppose we got the slope of this line x1 y1 and x2 y2. The slope of these two lines xa ya xa yb, this line, and xe yc xd yd can be calculated, because from simple geometry it is clear that these two lines will be perpendicular to each other. So the slope can be calculated for these two lines. And similarly, since we know the distance, the d value, we know the point and we know the slope, so the equation of this line can be easily calculated. Equation of line xa ya xa yb and equation of line xe yc and xd yd can be easily calculated. Now once the equation of these lines have been calculated, we know the equation of the circle with center x1 y1, center x2 y2, and radius d. So basically with diameter d, so basically the radius will be d by 2. So the equation of this circle can be constructed, and the equation for this circle can also be constructed. So when we find the points of intersection of the equation of the circle and the equation of this line, and equation of this circle and equation of this line, the particular coordinates xa ya xa yb xe yc xd and yd can be very effectively calculated. And so once these points are calculated, these 4 points shown in red, once these points are calculated, we can make a polygon, a rectangular polygon with joining these 4 points in lab view. And after joining these 4 points, we have now constructed a complete oblong, this capsule like shape. We can construct circles at this center, another circle at this center, and we can construct a polygon at these points. So once all these tasks are done, a track is being realized in this capsule form of shape. And once this track has been realized, so what we see is this track has been realized using just 2 points, x1 y1 and x2 y2. And similarly, we can construct as many tracks as we want, harnessing the D data and the x1 y1 x2 y2, which are readily available in the Gerber format. So what we basically want right now is that if we specify this distance, means this length d, and if we specify 2 coordinates x1 y1 and x2 y2, so we want to calculate these 4 coordinates xa ya, xa yb, xe yc and xd yd, and using and after when we have extracted these 4 coordinates, we can reconstruct this complete track. So the following VI will be in the following VI we will explain how this thing is done. So what we have right here is the block diagram of the VI that generates the 4 coordinates that we want out of the given data. So what the given data according to the figure over here is, the given data must be x1 y1, x2 y2 and the radius. Basically it should be d by 2. So these are the data we want, and according to these data we need to calculate the values of xa ya, xb yb, xe yc, xd yd. So this is what is happening in this VI, this particular VI. We are giving the radius, we are giving the value of x1, y1, x2 and y2. So within this VI there are various sub VIs have been created, like this particular VI. This particular VI calculates the slope of given x1, y1 and x2, y2 values. So this particular sub VI gives the slope of the line joining x1, y1 and x2, y2. And then we need to find the slope of these 2 lines, basically these 2 lines, xa ya and xa yb, xa ya, xb yb and xe yc, xd yd. So simple geometry confirms that these 2 lines are perpendicular to this line. So this particular VI calculates the slope of the perpendicular to the line. This particular VI, this one, it calculates the slope of the perpendicular line, as can be seen. So once having extracted all this, now we need to find the point of intersection, basically. So once the equation of these lines have been found out, this line and this line, we need to find the point of intersection with the circle, this line with this circle and this line with this circle. So so this is the line and this is the equation of a circle. So when we solve the equation, what we'll basically be getting is a quadratic equation. So to solve that quadratic equation, separate VI has been made. This VI, as can be seen, yes, it has math functions. Basically we are passing a formula here, and this is the formula for the circle, and this is the formula for the particular length. So we would be using the math formula, the math function. This is a math loop, and we will be using this loop to find the points of intersection. So once that they have been found out, we'll solve the quadratic equation. This particular block here, right here, this particular VI is for solving the quadratic equation. Based on the formula, we need to find the determinant, no, not the determinant, the b square minus 4ac value, and just doing the particular calculation out here. So these have been sub VIs have been made, because when we include all this, the total mathematical calculation and the representation becomes a lot cumbersome. So that's why these particular things have been created into sub VIs. So this will generate the 2 quadratic equation values, which are the particular coordinates. So we have 4 coordinates, and then we will be finding out those coordinates, because these are the particular x values only. We need to find out the y values also, because as seen till now we have calculated the value of xa, xb, xc and xd. and now we need to determine the values of the particular y coordinates. So here for the for the line for this line, for line this one and for line this one, the separate equations y is equal to mxc has been given in a math loop, and the particular y will be determined for each of them, and so later they will be means like put along in an array. So now finally we have four coordinates, which the four coordinates are our xa ya, xb yb, xc yc and xd yd. So as can be seen that this particular block, this complete block, takes the radius, the point A, which is x1 y1, the point 2, which is x2 y2, and gives out the four coordinates that we want to generate the complete aperture. So later on, even this complete vi can be condensed into a smaller sub vi and can be later on be implemented into our final block. So similarly, in this way we can combine multiple tracks, as can be seen in this figure. Here this circle and this circle and the polygon that is created here, that has been a single track, and the same circle and another circle and another polygon has been another track. So the combined polygons of these two, these combined oblong shapes of these two combine to create a complete new track, which is the track what we want. So this will be the active copper region. The whole complete area will be the active copper region that we want. So when we look closely at the Gerber file as it is seen here, when we look at the top of the Gerber file, as we can see here, there is certain format data. The format data usually specifies like in which format the Gerber has been created, whether it is created in inches, whether it is created in mm, whether it is omitting the zeros, whether it is leading the zeros, and etc. And following this are some aperture files, means the basic apertures, user defined or standard apertures that are in the Gerber file. So here we can see like two rectangular apertures are there with their dimensions. This is the length of the rectangle and the breadth, and similarly there are two rectangular apertures, and similarly there are some circular apertures with their dimensions specified. For example, this is the dimension for aperture D12, and this is the dimension for aperture D13, and so on. So basically these are all circular apertures and these are rectangular apertures. And as we look down, we can see that there are certain times of extrapolations for certain for all the defined apertures. For example, for D10 there has been extrapolation for some 3 coordinates, as it can be seen. For similarly for D11 there has been extrapolation for only a single coordinate, and similarly for D12, as we can see, it has been repeated for some n number of coordinates. Similarly for D13 sometimes, and as we go down there are repetitions for all the apertures that have been mentioned. So once all these coordinates have been extrapolated, the final image is realized. And also I would like to bring the attention to the coordinate file actually. So here every line, as we can see, the coordinate data has some part of x which specifies the coordinate of x when followed by some number. So this is basically the inch specification, and similarly after y there is some specification, means these are just basically the coordinate data on the Cartesian plane, the particular point which it is to be mentioned. But also we see that there are some data of D02, D01, D03. So what D02 and D01 means? So what D02 actually does is that D02 is like a lights off move. It is similar to moving a pen from one point to the other, like lifting it. Means this move does not create anything. Basically you're just moving from one point to the other point. So D02 means you're moving from the previous point, which happens to be this point, to the current point without creating anything. So you're just lifting the point to the current point. And similarly in this case D01 is the complete opposite. D01 means you are moving from the previous point, which happens to be this point, to the current point, which happens to be this point. So this is the interpolation move. So basically this moves creates the tracks, means from this point to this point, when you're extrapolating this particular aperture, you have created a track. So D01 basically what means is that you are creating a track by extrapolating from the previous point to the current point. Whereas D03 is completely different. D03 means like replicating. So D03 means whatever aperture there is at whatever aperture it is D10. Let us assume it's a circular aperture. So D03 means that this circular aperture will appear at this point, and this point. So means wherever there is D03, it means that that particular aperture is going to appear at that particular point in the plane. So far what we have seen is that when we look at this Gerber file, it is basically just coordinate data and some format data. But what interesting to note is that each and every line of the Gerber file actually represents some particular data. Means this line represents an aperture, other line represents an aperture. Each line of these represent format specification, and each of these are coordinate data. So what we can conclude is that each line of the Gerber file actually gives us some form of data which needs to be properly reconstructed to achieve the final image. So what our first task at right now would be to create a VI which gives the text file, means the Gerber file, as an input, and then the VI segregates each and every line of the Gerber file. So what the output will be getting is in the form of an array, and the size of the array will be the number of lines which the text file has, and the output means the array. Each element of the array will be the corresponding line, whatever there is. Means the first element of the array will contain G75 star, and similarly all the data. So when we process each and every element of the array that has been generated, we can harness the aperture data, the format data, the coordinate data, and we can then properly reconstruct all the final image. So right here we have the VI, which is used to segregate each and every line of a string. So here is the VI, this is the corresponding block diagram, and here is the front panel of the block diagram. So we'll directly jump onto the block diagram and see how it works actually. So here we have the block diagram. In the block diagram, the first part is that we are accepting the path of the text file, like where it is located in the directory. We'll take the path of the text file from the user as input, and this block reads the input text file, the existing text file. So it will give us the output in the form of text. So here we are running this part, we are running the string length. This will gives us the length of the string, and we are running the for loop, the length of the string times n times. So if the string length is n, so the for loop will run n times. So basically here the string will be as the input, and it will be iterated alphabet, means every character by character. So here the first character will come, then the next character. So this is the first character, and we are determining this is the this VI particularly this block particular concerns with the particular element, means if we want to the particular character of the text, like the second character, third character, and that's why we've connected to the ith iteration. And here we have some type def conversions. This one particularly is important because it converts the equivalent of the carriage return to ASCII. So the string is matched to the equivalent of the carriage return, and when it is equal to, means, and when it is true, means when the carriage return has been detected, then the output string is then the ith iteration, means the iteration in which the string has the carriage return has occurred, is sent to the output, else a 0 is sent forward. So basically an array is built up of zeros and the iteration at which the carriage return is detected. The final array is sent, and now in this block, in this particular block, all the zeros are omitted, because basically we are only interested in the intervals, means in the iterations where the carriage return occurs. So basically this particular block omits all the zeros in the array. So now when we have the final array, but there's a problem in this array. So if we see our text file, any particular text file, let's look at this file. Basically there is a carriage return here, 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 and in every line, but there is no carriage return in the last line. So we need to include the last line as well. So this particular block that we have here, this particular block take cares of inclusion of the final line. So after calculating, the number of lines is given and then we reconstruct it. Here there's a shift register, means the previous iteration, means the previous time where there was the carriage return, and the current time where there is a carriage return. So it gives the length, and at that time we can reproduce that particular string. So in this way we get the final output string here. So now we will be running this string segregate VI, which we have created here. This is our block diagram and this is our front panel. So we will be running this file, executing it, and see if it's work or not. So we will give the path of an input text file. I have created one on desktop by the name test. So this is the text file, and now we'll run it. So there it is. It has given the number of lines in text file is 10, and if we confirm it, it is 1 2 3 4 5 6 7 8 9 10. Yes, it is 10. And also it has given us the segregated string as well, means this array, this particular array is each and every element of the array. So at 1, at 0 we have this name Jayan, and at 1 we have the next line Kumar, next Yadav, the next line, next, yes. So as we have seen that now this VI gives us the each and every line of an input text file. So it also gives us the number of lines in the file, and also it gave us the each and every line of the text file, of the concerned text file. So now it is time to combine all the pieces of the puzzle together and to generate the final VI. So here we have in front of us is the block diagram of the current progress that has been made on the VI. So this is the block diagram, and here we have is the front panel. So there's the front panel, this is the block diagram. So we will focus on the block diagram that has been created as of now. So in this block diagram, as we can see that there are two sub VIs. We have one sub VI over here, and we have another sub VI present over here. So this sub VI, as we have here, is nothing but the VI of the string segregation that we made earlier. Here we have it. So since this will be a large block in itself, including it into a larger block would create some space constraints. So therefore it has been condensed into a sub VI. And similarly this one, as we discussed earlier, this one is the coordinate determination of the apertures. We had two circles and we had to determine the 4 points of the polygon. So this we have here. So these two VIs have been condensed into smaller sub VIs to save space. So here we give the path of the file here, we get the string, we get the segregated array, and we get the number of lines. So we are running this loop a number of n times, basically the number of lines, because we need to process each and every line, and here we are giving each and every element of the array, and this is a string of, it's an array of string, and each element in this array is the particular line. So at one time one line will be coming and it will be processing. So what we are doing right now is we are not processing any format data, we are only processing the coordinate data. So this part, this particular part extracts the x coordinate, this particular part extracts the y coordinate, and this particular part, the bottom part, this one, this part, this extracts the d, whether it's a d0, d1 or d2, d0, d1, sorry, d1, d2 or d3, yes, those coordinates. So till now, since we haven't extracted any format specification, I have included a boolean which will specify whether the input is in inches or mm, and based on that it will doing the conversion. So whether if it is in inches, so it will be converting to mm's, and if it is mm, it is giving output directly. So the coordinates, as we can see, the coordinates come, and when the coordinates get out after the coordinate matching to mm's, they get forward to the aperture create, and the same coordinates have been assigned to a shift register, because we need to create apertures one after the other, because the end point of one aperture will be the beginning point of the second aperture if we want to create. So this how. And so here 4 points are being generated and which have been combined here to create a polygon. So this one is for the creation of the polygon. Here these 4 points have been given into the create polygon, and this one is actually creating 2 circles. So we have taken an initial image out here, a blank image that comes, and the pointer moves to that. The 2 circles are created, and then the image is given to the create polygon. So we are getting an aperture. This code is run the number of times the string there is, and the final image is being realized over here. So we'll be now doing a small demonstration on whether, just to check if this works or not. So we'll be putting this aside and we'll come to the front panel. So I have a text file ready of coordinate files. I'll search it. It's on desktop. Yeah, this one, and I'll run. So it is processing. Basically it takes a little time. Yeah, it's been processed. Oh sorry, there has been some problem. Actually it needs to be okay. We forgot to give the radius. So now we'll be specifying the radius for the image, which we forgot to do last time. We'll open the code again. So this here is our front panel, and back this is our block diagram. We'll minimize the block diagram for now. We'll specify our Gerber input. So this Gerber is just basically the coordinate data, and now we'll be giving it a radius. I'll give the radius as 2. This is 2 mm because we selected in millimeters, and I'll be hitting the run button. So it will process according to 2 mm of diameter of the particular apertures. So it will take a little time, a few seconds. Yeah, there we have. Yes, so we have a final image here that has been created according to the coordinate data. So as we can see that when we specified the input text file, it has extracted all the strings. Basically this was the input string. As we can see, it was complete coordinate data, and it has given us all the a segregated array, and each element of this array is nothing but a line of the input string, which was basically coordinates, as there they are. So based on a coordinate pair, apertures have been created, as can be seen here. Tracks have been realized. So we will try to match it against the original PCB file. So I'll open it. So this was our original PCB layout file. Blue is the active copper region. These are the pads and vias, and we'll compare it with the layout that has been reconstructed by using the coordinates. So this, here it is. It is actually inverted according to the Gerber. The Gerber has inverted it. So it is moreover the same, but little refinement needs to be done based on the resolution, and also we need to make it monochrome. So now after a little refinement, it can be concluded that we can generate a final image. Basically we can reconstruct a final Gerber layout using just the coordinate data from the Gerber file. As can be seen, this is a particular layout, and when we compare it with the one that had been created here, there we have. Yes, so they are moreover like the same, but with just minor tweaks needs to be done on them. Yes, as can be seen now. So based in this way, we'll be generating a final image of this Gerber, and then that image will be sent for image processing based on edge detection, which is coming in the coming section. So that's how we have created a final Gerber using just the coordinate data from the text file. So previously what we saw was that we had created an image of our file. We basically reconstructed the aperture of the PCB from the Gerber file, and that final image had been created. So as of now, we'll assume that we have a PCB that has been created to us already. So we will be having an image. So let us have an image ready of a PCB. Let's say we have this PCB. So this is a monochrome image. It is basically black and white. So we will assume that image has been ready to us, and now we'll be running the edge detection on this code. So we'll be giving this image file as the input, and we'll be running the edge detection, the image processing on this particular file. So a separate VI has been created for this as well. This is the edge detection. We're using the Canny's edge detection method to determine the edges. So this here is the image. Yeah, this is the front block diagram, and we will, this is the front panel, and this here is the block diagram. It's a pretty small block diagram, which makes it very efficient. In LabVIEW, since we have pre-prepared modules, so it makes it very easy to accomplish the task first hand. So we didn't require to make a complete scratch code to implement the edge detection. So now we will source the input file, which is the PCB JPEG file. There it is. We have inputted, and now we'll run. So there we get it. We have got the edges. Basically what we can see here is we have got the edges of the concern, and that is exactly what we want, because our cutting tool will be running through these edges. So it will be removing this concerned copper region, and then what is left is the concerned copper tracks that we want. So that is how the final PCB will be realized. So we have all the edges prepared. Now what needs to be done is that this particular image, the image that has been created now, this outline, this will first be segmented, because we first need to know each and every contour and each and every outline, and then after according to the specified resolution, the particular coordinate will be extracted of each and of the edges, and that coordinate will be sent to the MyRio board for running of the stepper motors, because we will be using 3 stepper motors for 3 axes, which will be running on the XY plane to implement the job on the workspace. So and the cutting tool will be running over these edges, these specified edges. So that's why we need to determine the coordinates, which is for the later part, for later image processing. So that is how the edge detection has been done. Here we had assumed that we have a PCB aperture ready, which we did in the previous section. We had created an image. So if we assume that this was the readied image, so edge detection can be very effectively done.
So basically right now we have compiled up everything, and what on the screen right now here is the initial VI, which is used to send the command to the microcontroller, which is connected through a serial interface to the computer. So here is the front panel, as it can be seen. Here the visa resource name is to be given, the particular delay is to be mentioned between the steps, the number of steps to be executed is to be mentioned. We have a Boolean toggle switch, which is used to select between clockwise and anti-clockwise step. There is a stop button for the entire operation to stop, and this is the string which is actually being sent. So it is anti-clockwise, off is anti-clockwise. So A, next step is T. We are sending a delay of 50. So 3 times in the digits is 050. S, number of steps, and then the number of steps to be executed is like 900. So this string will be sent, and this is the string read, which basically is the UART read, what it is reading from the hardware. And so now at the here is the block diagram. Here are the visa read, and this is the visa write. So, and this one particularly is the mechanism through which we are sending our data. We have selected the baud rate to be 9600, and here I have connected the arrangement through a USB webcam, which can be viewed parallelly. So here is our arrangement, here is a stepper motor, here is a communicated FT32 through the PC link. This is our TechMega32 board, and here is the motor driver. So we'll be now directly be visualizing what will happen when a command is sent. So here I selected COM7, and I have given a delay of 50 right here. So I have given a delay of 50, and I have given let's say now, since it is a 200 step stepper motor, so basically it must execute one revolution in 200 steps. So I have given 15 millisecond delay between, and a total number of 200 steps. So it must execute one complete rotation. So I'll hit the run button. So yeah, as you can see, one complete rotation has been executed. Now similarly, this can be visualized on anti-clockwise. So here I have clicked on anti-clockwise and I rerun it again. So here it is executing anti-clockwise, and it will do it for one complete rotation. Okay, so with that done, means now we'll go on a little tweaking, like what can be done more. So I'll now means make the steps 400 and I'll make the delay a little smaller. I'll say it to be 20 seconds. Same, anti-clockwise only. So now when I run it, yeah, you can see it becomes a little faster, and now it executed 2 revolutions. 2 revolutions has been done. I'll say repeat the same for clockwise. Stop and I'll run it again. So now it is a little faster since I've reduced the delay, and it will execute 2 rotations now. Okay, so similarly we can means like achieve whatever steps you want with whatever delay and with whatever direction you want, it can be done. So if you want to run the stepper motor at maximum speed, this would be here for speed 3, and for say if I want to execute some 600 rotations, so it will execute 6 rotations now. It would have been a little difficult to see here because of the camera, but still it perfectly executed 3 turns. So now just to visualize whether it means the steps, right now I'm giving only 10 steps, and I'm giving a considerable delay for just to view. So I'll give a delay of 100 milliseconds between the steps. So I'll run. That was still a little invisible. I'll increase the delay. I'll make it 500, and I will run 10 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 10 steps have been executed perfectly. And similarly, if I wanted to make it anti-clockwise, I will just turn this knob on, and then I will run for again 10 steps with 500 delay anti-clockwise. Never mind, I'll run it again. Yeah, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. So as we can see that it is executing the number of steps associated with the number of delay and along with the specified direction perfectly. So in this way, since it is only connected to one of the port of the AVR board, so currently as of now we are using the AVR board because of unavailability of the NI Rio board. But once when we have the hardware, this whole arrangement can be implemented on the NI Rio because since it VGA platform, these things can run board only on one port. The stepper motor was been connected. We can connect a multitude of stepper motors to work as actuators, which when connected to the gantry, it can make the hardware move. So this was the complete setup demonstration.